Welcome to Calculus. Today we will investigate applying derivatives of trigonometric functions, focusing on the derivative connection among position, velocity, and acceleration in spring motion. So let's take a look at our one example. It does have 6 parts, so we'll begin here just by reading about this object. It's an object attached to a coiled spring, and it is pulled down a distance d 5 centimeters from its equilibrium position and then released. So you can imagine if I had a spring and had an object hanging at the bottom of the spring and I extended it and let it go, it would return to its equilibrium, bounce up, bounce down, bounce up, bounce down, bounce up. And that's this motion that we call simple harmonic motion. So the motion of the object at time t seconds is simple harmonic. Again, just means it goes from a low point to a high point and then oscillates back and forth between those. We've seen that happen with a spring. We can model that motion with d at t equals -5 cosine t. And that's our position function. So the first question here in part A is, as time varies from 0 seconds to 2 pi seconds, so that'd be about 6.28 seconds, how does the length of the spring vary? So we really need to look at a table for the distance or the position. So we'll start off, let's just say that this is going to be an answer we'll get from our table. So we'll put time, and we're just going to vary it from 0 to 2 pi. I see my x-axis here on the graph goes every pi over 4, but I'm going to go pi over 2 because we can see the pattern if we use those, and we got to go all the way to 2 pi. So we'll go 0, pi over 2, pi, 3 pi over 2, and finally full circle at 2 pi. So our function, again, it's the d of t, which is the position function -5 times cosine of t. And I'm going to label that position because we're going to make a connection in a moment from position to velocity and then velocity to acceleration. So we'll calculate here. So here I'm going to plug in 0 for time. So -5 times cosine of 0. Cosine of 0 is 1. So that's -5 times 1, which is -5. And that makes sense. That's the position 5 centimeters below equilibrium. At pi over 2, we could calculate -5 times cosine pi over 2. And cosine of pi over 2, that's at 90 on the unit circle, is 0, because that vertical 90 position has no horizontal component, so that's -5 times 0, which is 0. So at pi over 2 seconds, the object has returned to the equilibrium spot, the middle position. At pi seconds, so at 3.14 seconds, it's -5 times cosine pi. Cosine at pi is -1, so that's -5 times -1, that's +5. So at that point, the object has gone from time 0 below, hit equilibrium, now it's above equilibrium at a position 5 centimeters above it. See if you can predict what's the place at cosine 3 pi over 2. So that's that lower 90. That's again 0, so -5 times 0, so back to equilibrium. You can see this pattern forming, the -5, 0, +5, 0. What do you think the next one should be? Let's calculate. So -5 times cosine of 2 pi. 2 pi, the cosine 2 pi is +1, so that's down to -5. So I think probably you did predict that would be -5, and that really continues forever. So I do see in part F, I need to graph all these functions. So to answer part F, but also to answer part A, let's graph this. So I see on my y-axis, I got kind of a bad scale. It only goes to 2. So I'm going to rewrite the scale to be 2.5 all the way up to 5. Same in the negative direction. So negative 2.5, and then down to negative 5. So that'll let us graph all of our functions. So this is the position function. At 0, it's at negative 5. At pi over 2, it's at 0. At pi, it's at positive 5. 3 pi over 2, it's back at 0. And then at 2 pi, it's down back at negative 5. So this is the graph of the position function. And it shows what we would expect from a cosine with a negative coefficient. And that would continue to go. I'm just going to say that with an arrow down there on the right. So in terms of how does the length of the spring vary, it starts at the negative 5, it bounces back up to 0, rebounds up to positive 5, back to 0, down to negative 5, and so forth. Just oscillates between negative 5 centimeters below equilibrium to positive 5 centimeters above equilibrium. Part B then changes gears. It says, okay, so you've found stuff about the position. That was part A. Part B is then saying, okay, well, what is the velocity? So the connection we need to make is that the velocity of a function is really the derivative of its position function. So I want to take the derivative of negative 5 cosine t. So remember from our derivative rules for trig functions, that's going to be negative 5 times derivative of cosine is negative sine of t. So it turns out my velocity function is going to be positive 5 sine of t. Now we're looking for when the speed of the object is a maximum in part C. And we could do that in different ways. I think since we've got to graph the velocity function anyway, that will tell us where the maximum speeds are. So here, I'm just going to again create the same domain, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And let's again just calculate this function, and we're looking for what are the maximum y values. What's the maximum speed? I'm going to mark this. This is the velocity function, and it is 5 sine of t. So let's calculate 5 times sine of 0. So sine's different. At 0, sine is vertical component. At 0, the vertical component is 0. So this has value of 5 times 0, which is 0. At pi over 2, sine of pi over 2, so that's the 90. There, sine has a value of 1. So that's going to be 5 times 1, or 5. At pi, sine of pi is back to 0, again, because that's got horizontal component 0. So again, you can start to see this pattern forming. We're oscillating. It's just we have a different starting place. So from 0 to 5 to 0, see if you can predict the next value. So it's 5 times sine of 3 pi over 2, which is going to be 5 times, so 3 pi over 2 is the lower 90-degree angle. That's negative 1. So that value is negative 5. And then again, once we hit 2 pi, sine at 2 pi is back to really the starting place at 0. That's equivalent, 0 and 2 pi. That's going to be, again, 0. So 5 times 0 is 0. And let's go ahead and graph that one since we need to do so for part F anyhow. So it starts at 0, 0. This is a sine curve. At pi over 2, it's at 5. At pi, it's back to 0. At 3 pi over 2, it's at negative 5. And then at 2 pi, it's back to 0. So here's our velocity function. And just like our other one, it continues forever. So we need to answer the question in part C, when is the speed of the object a maximum? Well, that's at these spots. So it's a maximum here. It's also going to be a maximum down below, because remember, speed doesn't have a sign. Speed is a scalar measure. It doesn't have a direction. So really we're just looking at absolute value. So it's got max values at really those places when the object is back at the original position. Its speed is lowest when it's down pulled below because it's changing directions. High speed is when it hits zero and then rebounds, slows down, speeds up as it passes equilibrium. It's at a max, slows down, and that continues forever in that oscillation. To answer the question, though, we should be specific about the times. So let me record in the red here. So the time would be, I can list a few of them out, pi over 2, 3 pi over 2. And if we wanted to generalize to be able to kind of wrap all those pi's over 2, it's odd values. So I could say that this is 2k minus 1 times pi over 2, where k is a positive integer. And that would just ensure that I have a constant coefficient that's an odd number starting with 1. So to go 1, 3, 5, 7, 9, 11, so forth to infinity. So that takes us now to part D, where I want to find the acceleration of the object. So recall from our work with rectilinear motion that if I'm looking now for the acceleration, that again is the derivative of velocity. So I'm going to take the velocity function, which we just calculated to be 5 sine of t, and take the derivative of that. So that's going to be 5 derivative of sine is going to be cosine of t. And that again, that's my answer to part D, but then I want to figure out, okay, when is acceleration equal to 0? We'll do that with our last table, our last graph. So here I'll put time, same domain, 0, pi over 2, pi, 3 pi over 2, 2 pi. And I'll put the function, so acceleration over time is going to be 5 cosine of t. And we just want to calculate, again, we're looking for when is the acceleration 0. Plug in 0, so 5 times cosine of 0. So again, we're changing our view. We're looking at cosine, which is horizontal component. At 0, it has a horizontal component of 1. So that's 5 times 1, or 5. At pi over 2, that's the vertical 90-degree position. So cosine there is 0. There's no horizontal component. 5 times 0 is 0. At this point, you can probably start to predict what the values are. Now we'll plug in pi, 5 times cosine of pi. So pi is over here in between quadrants 2 and 3, so it's negative x value. Cosine at pi is negative 1. 5 times negative 1, negative 5. What's the next output, do you think? Use those patterns. So 5 times cosine, 3 pi over 2. 3 pi over 2 is this lower value. So again, there's no horizontal component at the 90s. So that's 5 times 0, which is 0. And last value here, 5 times cosine of 2 pi. 2 pi is back to 0. So again, that's cosine value of 1. 5 times 1 is 5. So I'm going to graph this, and that'll give us a chance to say when is acceleration equal to 0. So acceleration starts at positive 5 to 0 to pi at negative 5 to 0 to positive 5. And here's my acceleration curve. And just like the other two, it continues forever. You can see that when we're dealing with trig functions, really, they're all the same curve. It's just they've been shifted horizontally. In fact, sine and cosine themselves are the same curve that just show that shift left and right. So we've done everything except for finalize part E. When is the acceleration equal to 0? So those times, if I list them out, are going to be pi over 2, comma 3 pi over 2. So what we're seeing is that when the speed is a maximum, the acceleration is 0. It's an absolute kind of minimum value. So we could write it in the same way. It's 2k minus 1 times pi over 2. Same deal, k is from the positive integers. And that wraps up our investigation here of this motion model for an object kind of hanging at the lower part of a spring showing simple harmonic motion. So thank you for joining for this investigation of applying trig functions and their differentiation to real life scenarios. Let me let you solve your own real life problems. Thank you for joining. See you soon.